Are there any questions related to the previous lecture? Okay. Okay, I will take care of the Zoom thing after the lecture again. I don't know why for most of the students it's working this time, but for couple of you are still saying there you are facing a problem. But I will take care of it after the lecture. Uh, yeah. Hopefully, most of the students are able to join. Okay, and I will anyway upload the lecture video. Okay. So the last bit with -222 confused me. Okay. Okay. So, are you talking about the range of the binary number which is represented in two's complement form? Are you talking about that? Okay. Okay. So if that is the case, let me do an example for you and then you will understand. Okay. Uh, yeah. Okay. Okay. So let me then go back to the notepad and do an example for you. Okay, let's say that we have a 3-bit binary number, right? So if we have a 3-bit binary number, uh, like let's say bit 0, bit 1, bit 2, right? So, and let's say we are talking about unsigned numbers. So we don't have we don't cover negative numbers. We cover only positive numbers. So what are the all possible combinations for 3 bits? Values for 3 bits like 0, 0, all zeros, then 0, 1, then, oh, sorry, 0, 1, 0, then 0, 1, 1. Everyone can see my notepad, right? If not, please unmute yourself and let me know. So I'm just writing down all the combinations of binary uh, values for 3-bit number, and then I will explain, right? So we have 8 combinations. Okay. Okay, you can see. Okay. So these are the 8 combinations we have, right? So if I write the equivalent decimal value, what they will be? It'll be 0, 1, 2, 3, 4, 5, 6, and 7, right? So what is the range? The range here is 0 to 7, right? So which is basically 0, 2 to raise power 3 minus 1. Is that correct? So 0 to 2 raised power 3 minus 1, which basically is equal to 7. So this was about positive numbers, like, right? But when we say that we want to also cover the negative numbers, or we want to cover the signed numbers, so then it's mean that we will treat the most significant bit as the sign bit, right? So which bit is the most significant bit? Actually, it is this bit 2, right? So for half of the combinations, the most significant bit is 0, and for the remaining half, like remaining 4 combinations, the most significant bit is 1, right? So which means, like, if I'm treating the binary as a signed representation of signed number, then it is first combination is 0, next is 1, then 2, then 3, right? Now, what is uh what is this number? How can I convert it? So remember we said that the most significant bit is treated as sign bit. So it's mean that if it is 0, then definitely it will be taken as 0. So like if you add the weights for this number here, for this combination, it will be 0 plus 0 plus 0. Here it will be 1 plus 0 plus 0. Here it will be 0 plus 2 plus 0. And here it will be 1 plus 2 plus 0. So it becomes 3. But here the most significant bit is 1. So weight we have the same weight. What were the weights? Remember, the weight of the first bit is 1, the weight of the second bit is 2, and the weight of the next bit is 4. But since 1 is, now we are saying that binary number represents the signed numbers and most significant bit is the signed bit. So the weight will become -4, not 4, right? So when you add -4 plus 2 plus 1, what do you have? You have -1, right? And when you have in the same way -4 here plus 0 are the next combination, a combination of 101 plus 1. Why I'm writing here 0? Because this bit is 0. So weight 2 times 0 will be 0. So -4 plus 1, 1, 2, 4. -4 plus 1 will become -3. And -4 plus 2 plus 0 will become -2. And -4 plus 1, sorry, not plus 1, plus 2 plus plus 1 will become -1. By the way, here I did it wrong because here I'm saying that the values of the bit are 0, so it will be 0 and 0. Sorry for the mistake. So here it will be -4. So the range is from, now if you on the number line, if you draw it, so in the middle you have 0, on the rightmost position you have 3, and on the leftmost position you have -4, right? So the range is from 0 to raised to power 3 minus 1. Uh, you need to 3 minus 1 be, no, sorry. Let me undo it. So yeah, so 2 raised to power 3 minus 1, so it will be 2 raised to power 4, and then -1 here, and here it will be minus 2 raised to power 3 minus 1. Do you get it or not? Or did I make it more complicated for you? Sorry. Uh, okay, so please let me know if I have answered your question about this confusion about -2 to 2, how you calculate the range of signed numbers when they are represented in binary form. If it is still not clear, please let me know. If you are not comfortable like to write in the chat box, you can send me a private message. It's same in the chat box, but only directed for me. Okay, it seems like I don't know. I mean, the person who asked the question, I'm still a bit confused. Okay, so can you please elaborate a little bit what confusion you have exactly? So you can unmute yourself and you can talk. Do you hear me? I'm saying you can unmute yourself and then you can talk. It will be relatively faster as compared to writing text.
Um, can you explain how like the whole addition thing, like how you went from the 3 bits and like did you just make up those numbers or how did you end up with 100?
Wait a minute. Don't go away. Let do you see my notebook? My OneNote
Yes.
screen. So here, can you point me at what point you are confused? Are you confused here?
Yes,
100 at this point?
yes, like from the top, like from that place right there.
Okay, so 100. So this is just like this is the binary combination. What I did that I wrote all the combination of 3-bit binary values, right? From 00011110. First, I said that, okay, let's assume that we are using binary representation to represent only unsigned numbers. So we are not talking about negative numbers, right? So if that is the case, so all zeros is binary of decimal 0, 001 is binary of decimal 1, 010 is 2. Are you sure? Do you know how I am converting the binary from binary to the decimal form?
No.
No. So it's pretty quick. So pretty easy. How? So okay, let me give you another example, and then I will come back to this one. So let's say I have, give me any 3-bit binary number. Give me
One
any
two
3-bit
zero.
binary number. Sorry?
120.
No, binary number. When
Oh,
in binary numbers,
zero.
you can have only one or zeros. You cannot have
Yeah,
two.
001.
So 001. Let me make it a bit more interesting, because if we have only 001, it's trivial. Okay. So it is a binary number, right? So in binary numbers, what is the base of the system? It is 2, right? Just like in decimal system, the base of the system is 10, right? So how we convert this binary number into the decimal form? So to do that, what I do is, like, first I simply write all the binary digits, 1, 0, 0, and then 1, right? And then what I do is that, writing from start, I start multiplying them with the increasing power of 2. So I multiply this one with 2 raised to power 0, starting with 0. This one with 2 raised to power 1. Sorry, I'm writing it and in the lower line because I don't have enough space. This one with 2 raised power 2, and this one with 2 raised to power 3, right? Are you with me until this point?
Yes.
And then I simply take summation of the products. I sum all of those products together, right? So here
Yes.
2 raised to power 0 is 1, and when I multiply it with 1, I get 1. Then 2 raised to power 1 times 0 is 0. Then 2 raised to power 2 times 0 is 0. Then 2 raised to power 3 is 8, and times 1 is 8, right?
Yes.
So when I sum them together, I get 9, correct?
Yes.
So 1001 in binary is actually 9 in decimal system, right?
Yes.
Okay.
Okay.
Now come here, where in this example where we have all 3-bit values, like all combination of 3-bit binary, right?
Yes.
So doing the same procedure, you can see that all zeros is 0, 001 is 1, 010 is 2, 011 is 3. Let me also draw this line just not to confuse you. So here I have 1, okay? So 100
Yes.
is 4, 101 is 5, 110 is 6, and 111 is 7, right? Are you with me on
Yes.
that? I mean, I
Yes.
cannot do the math for all of them, but offline you can do it and you can confirm for yourself, right?
Yes, that makes sense.
Okay. Now, so we were saying it that here we are representing only unsigned numbers, which basically means positive numbers. Okay, but let's
Yes.
say we are using the binary to represent not only positive numbers but also negative numbers. So if that is the case, then what we do is that we say that the most significant bit of the number will represent the sign of the number, right? So which bit is most significant? This bit 2, right?
Yes.
Right? So in first
Yes.
four here, the most significant bit is 0. And in the remaining four, the most significant bit is 1. Here, right? This one,
Yes.
right?
Yes.
So now let me convert one positive number and one negative number for you. Okay? Pick any one of
Okay.
any one of these four. Pick anyone. Be quick, be quick. So we need to also
Pick
cover
any
the.
one of which
Sorry?
four of what?
Pick any one of the first four.
010.
010. Okay. So we said that we treat the first bit as signed number, as signed bit, right? So
Yes.
that, which means basically that the weight will become negative. So what are the weights? The first weight is 2 raised power 0. Next weight is 2 raised power 1. Next weight is 2 raised power 2. But we are saying that we are using the binary representation to represent signed numbers. So the most significant bit will be
Negative.
sign bit. But since sign it is 0, so we will treat it as positive weight, right?
Okay, yeah.
Just like we did earlier. And then you simply multiply with the bit values, plus 0, and multiply this one with 1, this one, that's basically. Then add
Yeah.
and multiply with 0. So this is like plus 2. So this will become
Yeah.
0 plus 2 plus 0, right?
Yeah. Yes.
Now give me any number from the lower four combinations.
110.
Okay. Okay, you said 110, right?
Yes.
So 110. Again, first weight is 2 raised power 0, second weight is 2 raised power 1, and next weight is 2 raised power 2, but negative 1, right? The weight will
Yes.
be negative, right?
Yeah.
So then simply multiply with them with the bit values.
Yes. That makes sense.
So this will be -4, this will be 2, this will be 0, and this will be equal to -2. So 110 is binary of, sorry for this bad rhyme, -2. Okay.
Yes.
Is it
Okay.
clear
Thank you.
now?
Yes.
Okay. 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 Now then we can go back to our today's lecture. Okay. Uh, okay. So I'm just reading this slide just to give you recap, and then we'll go to the following slides. So how we get the 2's complement of a number? To get 2's complement of a number, what we do is that we replace all zeros by ones and all ones by 0. Basically, we are just toggling the bit values of the binary number. So if we have the binary number uh, 0110, so we simply first get its one complement by toggling all of it bit values, so it becomes 1001, right? Now how to get 2's complement? By adding 1 into 1's complement. So this is 1's complement, and we will simply add 1 to it. So here this is what we are doing. We are adding 1 to 1, 1's complement, and we get 1010, right? So you guys know how addition in binary works or not? If not, send me a message and I will explain. If anyone doesn't know how addition in binary works, in binary numbers work, let me know. No, okay, you don't know, so let me explain that. Uh, okay, so again, so let's take the same example. Why can't I? Okay, so let's say I have this number 1001, and I want to add 1 to this, right? And this 1001 is binary number, right? And I want to add 1 to it. So if I add 1, 1 and 1 is what? 2, right? And what is the binary of 2? Binary of the 2 is 1, 0, right? So I write this 0 here, and this one becomes a carry. So it becomes a carry here, right? So 1 plus 0 is 1. So remember that since we are talking about the binary system, so we cannot have any figure bigger than 1, right? So that's why when we say 1 1, it becomes 2. So 1 plus 1 is 2. So when we convert to binary, it is 1 and 0. So we write 0 0 here, and we get the carry here. So now 1 plus 0 is 1. So here 0 plus 0 is 0, and then we have 1. Okay, so this is now 2's complement of the number. So this was 1's complement. We added 1 to it, and we get 1010, which is 2's complement of the number. Okay, clear? Any confusion? Okay, I am taking silence as a mark, like everyone is clear on the topic. Okay, and I'm continuing. Makes sense to me. Okay, good. So now here is an example. What is the decimal value of 0110001? So first, when we want to convert the decimal, if it is specified that the given binary number is used to represent the signed numbers, or even if it is not specified, we by default we assume that the most significant bit actually is the sign bit, right? So if it is sign bit, So first we look at the most significant bit. Most significant bit is 0. So it's mean that the weight of the most significant position, bit position will be positive, right? So it is a non-negative number because bit is 0, most significant bit is 0, right? Then what we do is that we want to convert 0, 1, 1, 0, triple zero, all one to decimal, right? So if we want to convert it into decimal, how we can convert? Actually doing exactly the same thing. I don't want to do on the notepad because it takes too long, but I can simply explain it to you. What you do is that you have the first weight. What is the first weight? 2 raised to power 0, which is 1, right? And then you multiply it with the bit value. So 1 times 1 is 1. Then this next four weights are don't matter, or we don't care about them because the bit values are zeros, right? So the first weight is 1, then 2, then 4, then 8, then 16, then 32, right? So we write 1 times 32 here. And then the next weight is 64. So 1 times 64. 64 plus 32 plus 1 is 97. Okay. And since the most significant bit is 0, so we know that it is a positive number, right? Any confusion or question here? Okay. How about triple one? I'm reading from the most significant side. So this is the most significant side. 1, 1, 1, all four zeros and then 1. So if we convert this, how we'll convert this into the decimal? Again, we first look at the most significant bit. Most significant bit is 1, which means that this number is a negative number. Okay. So most significant bit is 1, a negative number. So to convert this one, what we do is that again, exactly the same thing. So first weight is 1. So 1 times 1 is 1. Then next four bits are 0 in their values. So 1, 4, 8, 16, 30, 1, 2, 4, 8, 16, 32. So 32 times 1. Then next weight is 64. 64 times 1. And the next weight is 128. But it is not only 128. It is negative 128. Why? Because it is the most significant bit and it has a value of 1. So weight becomes negative here. So when you will add all these numbers together, you will find minus 31. So this is like binary, decimal equivalent of this given binary. Okay. So any questions here? And this is important to note here. This binary is equal to minus 31. It's not equal to minus 97. Don't make the mistake where what you do is that you use this most significant bit only for representing the sign, and then you use all of the remaining bits only to get the value. So basically what I'm saying is, don't, when doing the conversion, don't make this mistake where you convert only one and four zeros and 1 to decimal, which will be equal to 97. And then you look at only at most significant bit and you say, oh, this is negative 1, so it's mean the number is negative, so I can put minus 97. No, that is wrong, because you need to add you need to add the negative weight. Okay, not only the sign, just like I showed you here. You need to add the negative weight. Okay. So if the MSB is 1, that bit is negative. So let me state it correctly. If the most significant bit is 1, the number is negative. The number is negative, not that bit. The number is negative. So the weight of that bit position will become negative. Just like in this example, because the most significant bit is 1, the weight of the most significant bit position becomes negative, which is minus 128. Okay. Ah, okay. Okay. So here is an exercise for you. You have 2 minutes to do. Find 2's complement number of decimal number 12 in 8 bits in 2 minutes. So you have 2 minutes to do this exercise. So find 2's complement of decimal number 12. So you know the procedure, right? Let me give you the steps. First, get the 4-bit binary, 8-bit binary of 12, right? Then find its ones complement, and then add 1 to the ones complement of the binary of 12. Okay, start doing it. You have 2 minutes, and when you are done, let me know. And also write your answer in the chat box. I am not pausing the recording because then I forget after the example to resume it. Okay, let's wait for a couple of more students to finish. Okay. Okay, I still want to wait because 2 minutes are not completed. I want to give the other student also the full time to complete that exercise. Okay, thank you. Thank you for the solution, sorry, sharing your solutions. So let's have a look at the answer. So to find the answer, first we need to find the 12-bit binary of 12. Sorry, 8-bit binary of 12. So 8-bit binary of 12 is, I'm reading from the most significant side, 4 zeros, then 1 1 and 0 0. Okay, I'm not explaining again how to convert the decimal number into a binary number. You can simply do the repeated division, and if you don't know how it was, go please check the previous lecture and its video. Okay, so we converted 12 into the 8-bit binary number, and then we first find its ones complement. So when we find its one complement, it becomes this one. Basically, all the bits are toggled. So all zeros become one and all ones become zero. And after that, we add one to it. So when you add one to it, you will get, reading from most significant side, four ones, then 0 1 0 0. Okay. So, okay. Okay. Good. Good. Most of the students did a good job. Okay. Uh, Now, what about subtraction? Now, remember that uh, when we want to subtract two numbers, let's say a minus b, so it is equivalent of saying that you want to add a plus minus b, right? You want to add to the a the negative of b, right? Instead of saying a minus b, it is same process, right? So what we can do is, like, it is same. For example, in terms of binary, let's say you have two numbers 0 0 1, and you want to subtract from it another number 0 1 0. So what you will do is you can simply write 0 0 1 plus complement of 0 1 0. Now, in digital hardware, negative numbers are represented, as I have explained in the previous lecture. Negative numbers are represented by finding the twos complement of the number. So if I want to find twos complement of this binary number, what it will be? First, I will find its ones complement. So I will toggle all its bit. So it will become 1 0 0 0 1 1, and then I add 1 to it. So when I add 1 to it, it will become 1 1 0 0, right? So let me also do this. Sorry. Okay. So let me do this addition quickly here, just to again give you an example of how binary addition works. So here I have ones complement. I am adding one to it, right? So when you say 1 1, so it will become 2. So 2, the binary of 2 is 1 0, right? So I will write 0 here, and one will be, this one will become a carry here, right? So 1 1 again is 2. So which mean again I will have 1 0. So I will write 0 here and the 1 will become carry, right? And then 1 plus 0 is 1 and then 1 plus 0 is 1. So I get 2's complement as this value 1 1 0. And then I add 0 0 1 triple 0 1 to 1 1 0. So when you will do the addition, you will get 1 1 0 1. Okay. So that is how you can add do the subtraction. Basically what we are saying is like to do the subtraction, you can simply first find the 2's complement of the number and then add it to the other number, right? So okay, I think someone has posted the answer. Okay, so let's check if our solution is correct or not. So let's first convert 11012 to the equivalent decimal. So how we will convert? So the weight of the first weight is 1. So 1 times 1 is 1. We don't care about the second weight because the bit value is 0. So we can directly write 0. So 1, 2 and next weight is 4. So 1 times 4 is 4. And the next weight is not 8 minus 8 because most significant bit is 1, right? So it becomes minus 8. When you add all of them together, it will become minus 3, right? And you can also how you can verify if it is correct or not. So this is the answer you found here, right? The same answer. You can actually do the same thing here and then you can compare with the words. So 0001 is what? It is 1. And minus 0110 is what? 4. So you are saying 1 minus 4. So 1 minus 4 is minus 3. So it's mean your solution is correct because by both approaches you get the same value. Okay. Any questions? No? Okay. Okay, so this figure basically talks about the same thing, a same idea which I have explained earlier, right at the start of the lecture. There is some text. Okay, not yet. So just like at the start of the lecture, we were talking about the ranges of the range of a binary number. Like just like we said, if we have 3-bit binary number, so and this 3-bit binary number represents signed number, then the range will be from minus, what was that? From minus 4 to 3, right? So in the same way, let's say now if we have 4-bit binary number. So if we have 4-bit binary number, which is definitely represented as 2's complement. So if you have 4-bit binary number, what are there will be in total 16 possible combination of binary values. All zeros, 1, 1 0, 1 1, 1 0, and so on. 1 0 1, 1 1 0, triple 1, then 1 triple 0, 1 0 1, 1 0 0 1, 1 0 1 0, 1 0 1 1, and so on until you reach triple 1, right? So by using the same conversion method which I explained to you earlier, if you do the conversion, the numbers starting from this point, all zeros, and going down to this point, all of them will be positive. Why? Because most significant bit is 0, right? So this will be 0 and this will be 7, right? And then starting from 1 triple 0 to all ones, all these numbers will be negative. Why? Because most significant bit is in all these numbers, most significant bit is minus 1 is 1. So for example, if I convert this one, what will it will be? So I don't care about the initial weight because all three bit values are zeros. So 1, so 1 2 4 8, so minus 8, right? Why minus 8? Because most significant bit is 1, so weight becomes negative. And here it will be minus 8 plus 1, which will be equal to minus 7, right? And when you will keep doing this conversion, you will reach here. So the for 4-bit 2's complement number or 4-bit signed number, the range will be from minus 8 on the downside to plus 7 on the upside, or the upper limit will be plus 7 and the lower limit will be minus 8. Okay. Any questions? Okay, good. Okay, so this last slide is about ASCII code, which stands for American Standard Code for Information Interchange. So why we need this ASCII code? Because when we are working with a computer, we want to represent not only numbers. For example, when you are writing, let's say, a program, and you want to maybe in that program you are not only processing number, but you are also processing strings, right? Like for example, hello world, right? So we have talked about how numbers are represented. Uh, you can convert them in the binary, but then even before converting them into the binary, they have to have some code, like which is known as ASCII code. So for all of your characters on the keyboard, you have some equivalent code. So for example, let's say when you let me pick some number, like for example, some character, for example, A. So when you press A on your keyboard, the hex code, which is the value which is transferred to your digital hardware, is definitely not A. Why? Because digital hardware is it cannot recognize A as a character, as a symbol. So the what we do is that when we press A, the digital hardware will receive the binary of this hexadecimal value 41. So when you convert it into the binary, it will be like, let me convert. Remember from previous lecture, how can we convert? We replace each character in hexadecimal form with 4-bit binary. So 1 becomes 0 0 0 1, and 4 becomes 0 1 0 0. So in other words, what we are saying is that when you press A on your keyboard, your computer or your digital hardware will read this 8-bit binary number. Okay. So because it can recognize only binary values like zeros or one, it cannot recognize anything else, right? So that's why all the symbols on your keyboard, they have their equivalent code, which is listed in this table. For example, let's say you have the key 2 on your keyboard, so it will have the hex code of 32, but definitely the binary will be sent to the computer will actually recognize the binary, not the 32 hex. So this is only for our readability that we are saying a hex equivalent of its code will be 32, right? So in total, it is a 7-bit code, so which means that on maximum we can have a value of 7f, which is equal to the delete key on your keyboard. So when you press delete key on your keyboard, the binary of 7f is transferred to the digital hardware. Okay. Yeah. Okay. uh any questions? Okay. uh if no questions, then this is the last slide of this slide set. uh Now let me open the next set of slides. Okay. So in this set of slides, we will be basically talking about the internal organization of a computer. And here, when we say internal organization of a computer, basically we mean the internal organization of a microcontroller, and more specifically, the microcontroller we are studying, right? Uh, Atmel, what was this? Atmel 328P, right? So the topics we are going to cover are the different parts of a microcontroller. So for example, the component of the microcontroller which deal with input and output, its memory chips, CPU, and how these different parts are connected with each other on the chip of the microcontroller. For example, how we can connect memory to the CPU, or basically how memory is connected to the CPU, or how IO devices are connected to the CPU, and how a computer works, which basically mean that how data is moved around. For example, how you can send data from CPU to the memory, or from memory to the CPU, or from memory to the IO devices, right? And how can we perform the logical and arithmetic operations on the data. Okay, so this figure we have seen earlier, like in our first lecture. So basically, it shows the internal block diagram of your AVR microcontroller. So it consists of a It consists of a CPU, right? And within the CPU processing unit, you have different registers. We will talk about them later. And not only different register, you also have arithmetic and logic unit, a unit which is responsible for performing arithmetic and logic operations. Then you have so then you have data memory, so which is basically RAM or static RAM. Here they have not written as SRAM, but in AVR microcontroller it is static RAM. uh, Besides that, you also have program memory here. uh, so remember we said that program memory is read only. So what you do is that, remember in the last lab, or I guess you are still, some of you are working on lab 1, so you are supposed to download or burn your program in the memory of the CPU, in the memory of the AVR. So when you say burn it, basically you are writing the program into the code memory or the program memory of the microcontroller. And once you have written it there, after that, when your program execute, the program is only read from there. During the execution phase, you cannot modify the program memory or the code memory, right? And the AVR microcontroller is a RISC architecture. So what is RISC architecture? I briefly explained it in the previous lecture, but we will have more slides on it on the RISC architecture later on. Okay. Uh, so what is the job of the CPU in the internal organization of the AVR or microcontroller? So it performs your logical and arithmetic operations, and memory, it is responsible for storing, retaining, and recalling the information. So for example, uh, it basically it holds your data and your code, right? So the code memory holds the code, and your data memory holds your data, right? All the numbers you on which you want to do any kind of processing, they are read from the data memory, and after you perform the processing, the results are again written back into the data memory. However, instructions which you are executing, they are read from the program memory, and program memory is read only. You cannot write it. You cannot write it during the program execution. Definitely you can write it or burn it in the initial phase when you are downloading your program to the program memory of the AVR. And what are the input and output? So these are the devices through which your AVR microcontroller can interact with the outside world. For example, uh, an example of the input device is keyboard, mouse, or some kind of sensors. So in this course, since we are working with a microcontroller, we will not have keyboard or mouse, but we will be reading some input from sensors. Okay. Output, any kind of the device which can display the data which is sent by the microcontroller, for example monitor, printer, or hands of a robot. And in, for example, in this course we will be using, just like in the first lab, you are using LED as an output, right? So the data is sent to the LED by your microcontroller, and then it is just displayed. So it is by blinking, but when it is turned on, it's mean that data value of 1 is sent. When it is turned off, it's mean that data value of 0 is sent, right? So this is just a very trivial example of an output, right? But in the labs down the line, we will have other example. We will display our data on maybe on 7 segment display. Okay. Okay, memory characteristics. So we will now talk a little bit deeper for about each of these components like CPU, memory, and I/O. Right? Let's first talk about memory. Memory. So how we characterize the memory, right? So the first thing, or the first parameter which characterizes the memory chip is the capacity. So capacity is basically that how many bits you can store in a memory chip, right? Number of bits, not number of bytes. It is number of bits. Keep in mind that the capacity of memory is always given as number of bits. So if we say 128 kilobits, so it's basically mean 128 into 2 raised power 10, because 1 kilo is 2 raised power 10, 1 mega is 2 raised power 20. Okay. And 1 after mega is giga, I guess 2 raised power 30, and so on, right? So 128 kilobits is basically 128 times 2 raised power 10, which is equal to 128 times 1024 bits. You can do the math and you will find that, okay, this is the total capacity of your memory chip. And when I say 250, I have a memory with a capacity of 256 megabits. It's mean basically I have 256 times 2 raised power 20 bits. which is equal to 256 times 1024 times 1024 bits. So I have a memory chip with this number of bits. So I can store this number of bits in that memory chip. Okay. Okay, organization. So organization is basically that how memory locations are organized. Uh, so for example, if I say that we have a 128 cross 4 memory, so what information is conveyed by this statement? It tells me that in my memory chip, I have 128 locations, and their addresses are from 0 to 127, and then each location is 4-bit wide, which basically mean that each location can store 4 bits. So what will be the total capacity of the memory chip? It will be 128 28 times 4. So I can store this number of bits. So here is the graphical representation. So if I have 128 cross 4 memory, so I have 128 locations and they are addressed from 0 to 127, right? Because first location is addressed as 0, that's why the last location is addressed as 127, not as 128, right? And then each location here, you can see each location is 4-bit wide. So in each location, I can store 4 bits. So in total, I will have 128 cross 4 uh, bits, which I can store in the memory. Any questions? Okay. Uh, Access time. Another important characteristic of a memory chip is, so we have first talked about two things: capacity, which tells us how many bits can be stored, and organization, which tells about how the memory is internally organized, like how many number of locations we have and how many bits we can store in each location. Okay. So the next thing is access time, which is very critical, right? So access time, it is the time to read data from memory. Note, it is the time to read data from the memory, not the time to write the data to memory. Uh, because typically writing data to to memory is not important. The time it takes to write the data to the memory is not important from the perspective of CPU. Why? Because if, let's say, if you are running uh, and it has some couple of instructions, right? And let's say on this instruction X, you are saying, okay, write some data A into the memory. Let's say I'm saying put value A in the memory location X, right? You have some other reasons, right? So what the CPU please send the data X to the memory, sorry, simply send the data A to the memory location X, but you don't need, the CPU don't need to wait until the data is actually written in the memory. Why? Because I am not, if I'm assuming that I'm not using that data again, right? So I can continue with the next instruction without Okay, I think I was disconnected. Uh, okay. I am back. If you guys can hear me, can you please confirm? Okay, good. So let me again start sharing. Okay, so you can see the screen, right? Slides. Okay. So I hope we still have time. Yeah, we still have 5 minutes before we go for the quiz. So remember, I was saying that from the perspective of the CPU, the time it takes to write the data to memory is not important. Why? Because after putting the data on the bus, it doesn't care whether the data has actually reached the memory or not, right? But because once it has placed the data on the bus, it can continue with executing the next instruction, right? But when it comes to the read, it is a different story. Read operation, let's say I have some a program which is consisted of some instructions, and then I have an instruction which says, okay, read data from address A and put it in the in some register X of the processor, right? And then in next instruction I'm using that value which I have read from the register, right? So I'm saying, okay, in the next instruction here I'm saying use X, right? So this time the CPU must wait for a value data A to become available in the X, right? It cannot continue to the next instruction before the data becomes actually available in the register X, right? So that's why, so it's mean that the speed of my program, or that how long my CPU need to wait for that data to become available X, is critical, because longer it waits, if it longer it takes to complete the transfer of the data into register X, longer the CPU will have to wait, and it will slow down my execution, right? So that's why we say that access time is defined as time to read the data from memory, not the time to write data to the memory. Okay. And this is normally defined at nanosecond scale. So what is nanosecond? It is just like 1 second is 1,000 milliseconds. So milli means you have 1,000 milliseconds in 1 second, and you have 100. This is 1 million, right? Unit 10, 100,000, 10,000. Yeah, 1 million. So you have 1 million microseconds in a second, and you have this much nanoseconds in a second. So your memory speed is normally specified, access time is normally specified as in nanoseconds. Okay. Let me go through this slide and then we can stop. So this is normally how we connect CPU with the memory. So here on the right you have CPU, on the left you have CPU, and on the right you have the memory chip. And on the memory chip you have different signals. So let's start with the trivial ones. So you have ground signal which you connect with 0. You have the power supply signal or voltage, input voltage, and then other than that you have address input, right? And it is one way. It is because only CPU can read or write the memory. That's why address is always sent by CPU to the memory chip, right? So basically by sending the address you are telling that, okay, from which location I want to read the data, or to which location I want to write the data. So here, for example, remember we said we have like 128 locations. So if you want to read or write to the, let's say, location number 2, so here you will send the address to, right? And this bit, sorry, not bit, this bus is called the data bus, and it is two-way because data can be either sent, CPU can either read the data from the memory, or it can write data to the memory. That's why data needs to flow in both direction, right? Depending upon read or write operation, right? So here we specify the address, and here we CPU either puts the data or CPU gets the data from this bus, depending upon what operation CPU wants to perform. Now, how can we tell the memory, or how does the memory know whether from the address which is given, whether it is going to perform a write operation or read operation? So for that, you have control signals. So this is known as write enable. So if this is also sent by CPU, so if this is 0, and all of them are active low. Active low mean that a signal is active when it has bit value of 0. So when CPU sends here 0, it's mean that it is telling the memory chip that I want to do the write operation. And when it is sending 1, it's telling the memory chip that no, I don't want to do the write operation. And output enable is like read. So I want you to enable the data to be available on the output, which is the data bus, right? And chip select is to enable the memory chip as a whole, right? So all of these are low active signals. So basically, if you want to do a write, so you will write here chip select will be 0 and you will send 0 on the write enable. If you want to do the write read operation, then you will send 1 on the write enable and 0 on the output enable. Okay. So with that, let's stop, and I think you guys can go and start doing your quiz. Okay. Your quiz is released. Please go there and start doing your quiz on the canvas.